Okay, well, at the end of class today, we're going to do the first quiz. Um, that'll just be like the last 10 minutes of class. Um, so I just want to start with a couple of example problems, and then I'm going to keep doing this periodically throughout the semester, just do sort of outlines of what we've covered so far. This class is really kind of just about absorbing a lot of different like relationships and stuff. Some classes are just like you learn two equations and you just apply them a million different ways. This is kind of the opposite of that. It's throwing a bunch of stuff at you. So I'm going to keep giving these periodic outlines, and you should keep outlining yourself and keep going over these outlines as the semester goes on, just to try to store all this information in place, you know. Okay, so let me start with, yes.
For 5, since we're not given an H constant, we only use the radiation, right?
Let me look at it.
Or did we need to find convection too?
Number 5. This is not convection. It's not a moving fluid. It's just and anytime you're given the emissivity, the only thing that's relevant for is radiation. So if nothing else, you can just see that and know that we're talking about radiation.
Thank you.
Yep. Okay, so this is a convection problem. So let's say that we have a microchip embedded in an insulator. And a cooling fluid flows over the top of the microchip, just the top surface. So it would look something like this. You have this substrate that it's embedded in, and the chip, all you have in contact with the fluid is that one surface, and the fluid flows over the top of that one surface like this. The area of the chip surface is 5 millimeters by 5 millimeters. And the coolant temperature is 20 degrees Celsius. Electric power to the chip is 0.225 watts. It was determined experimentally that in this setup, the H constant is 150 watts per meter squared Kelvin. And if the chip is in steady state, what's the temperature of the chip surface? Okay, so remember that in the differential form of the first law, which is the form that we always use with these heat transfer equations, there are two types of problems that you can do. One is steady state. That's where you know that the form of this equation says dE dt is equal to Q dot minus W dot. Q dot is the rate of heat transfer into the system. W dot is the rate of work produced by the system applied to the surroundings. Steady state means dE dt is equal to 0. In fact, every property is constant in time. That's what steady state means. And transient means dE dt is non-zero. So I'm going to do one example of steady state, and then we'll do a transient one. Okay. So this is steady state, which means, so we have this equation, dE dt is equal to Q dot minus W dot. Steady state means that this is 0. And so we can write this as just Q dot is equal to W dot. We are told that the electric power is coming into the chip. So anytime something is powered by electricity, that's treated as power. And that's 0.225 watts. So W dot is equal to plus or minus 0.225. And now we have to think about the sign. So if work is being done on the system, is that positive or negative? Negative. And so we have that the differential first law says, so we have Q dot is equal to W dot. Q dot is equal to negative 0.225. And now we can think about that heat transfer. Since we're talking about fluid moving and carrying energy away from the system, this is convection. You can also tell that because we have this H constant. And so the equation for convection says that Q dot is equal to plus or minus H times the area that's in contact with the fluid times the quantity temperature of the body minus temperature of the fluid. We know we want the negative in this case because it has to match this negative 0.225. So plug in the H, that's 150. the area that's in contact with the fluid is just that top surface area. I could have made this slightly trickier by giving you all the dimensions of the microchip, and then you would have to know what surface we're talking about. But it says that this is a square, 5 millimeters by 5 millimeters. So that is 0.005 squared. And then the temperature, we're trying to calculate the temperature of the body, the chip. And we're given that the temperature of the surroundings, 2, yeah. So this is a difference in temperatures. So we could just keep it in Celsius, but putting it in Kelvin is fine. So I'm just going to put, what's going to be the higher temperature here, the body or the fluid? The body. So I'm going to write this as TB minus 20.
Professor,
Yes.
so like for the conduction one, we can just like change them around for like preference.
The conduction one,
This one.
oh, convection. This is convection. Yes, you can change them around. I mean, basically, like whatever sign you get from that equation, you're going to have to think about the meaning of the sign after the fact, anyways. You know. Okay, so we got 150 times 0.005 squared, and so Q dot is equal to negative 0.00375 times TB minus 20. And now put it back into the first law, and you get that negative 0.00375 times the quantity TB minus 20 is equal to negative 0.225. And so TB minus 20 is equal to 60. And so the surface of the chip has a temperature of 80 degrees Celsius. Okay? Any questions about that? Okay, yeah.
How did you know the Q dot was negative?
Okay, well, so starting with the differential form of the first law, in steady state, we just get that 0 is equal to Q dot minus W dot. And so the result of that for any steady state use of differential form of the first law is that Q dot is equal to W dot. And we were given enough information to figure out what W dot is. It said that electric power goes to the chip at this rate. And remember that the sign convention says electric power, power, work or work dot is positive if it's being done by the system on the surroundings. In this case, we have work being done by the surroundings on the system, so it's negative. And then from there, we just knew, well, if W dot is negative, then Q dot has to be negative. Any other questions? Okay, let's do a transient one. So let's say that we have 0.75 kilograms of material. Let me put this up at so in the example up here, notice that this is a steady state example. The one we're doing now is a transient example. So we have 0.75 kilograms of a material. And at time 0, the material has a specific internal energy of 20 times 10 to the third joules per kilogram. Electric work is input to the material, or I guess let's call that power, electric power. Power is just the rate of work. That's always what power means. So electric power is input to the material at 1 times 10 to the third watts. And heat is lost from the material at a rate of 5 times 10 to the second watts. So first, we want to calculate dE dt. And actually, we're going to assume that there's no change in kinetic energy, potential energy. So let's think of this as internal energy. So first, what's du dt? Second, what's d little u dt? So the rate of change of the specific internal energy. And third, what's the specific internal energy as a function of time? Okay, we're given everything in terms of rates, so it makes sense that we would be using the differential form of the first law. So the differential form of the first law says dE dt, which in our case is just du dt, is equal to q dot minus w dot. So that's sort of our starting point. Well, we're almost, let's see. So we're given some information about the internal energy, but we're not given the information about the true internal energy. We're given it for the specific internal energy. So the first thing we have to do is find that relationship. Okay. Well, the internal energy is equal to the mass times the specific internal energy. You know, the definition of the specific is the true per mass. So that means that this relationship gives us the true internal energy. And if you take the time derivatives of both of those, and mass is not going to be changing in time, we get the du dt is equal to the mass times little du dt. Okay. If we're being like careful about it, thinking about it carefully, well, this is the relationship. You would have to use the product rule to take the derivative. So you'd get dm dt times u plus m times du dt. But m doesn't change in time, so this term goes away. And we just get m times du dt. That's going to be useful in these differential problems. So I'm going to set this aside for a second. We'll come back to it. And now we'll set up du dt is equal to, we have to think about the meaning of these changes in energy. So electric power is input to the material at this rate. Does that mean the W dot is positive or negative? Negative, yep. So W dot is negative 1 times 10 to the third watts. And heat is lost from the material. So is Q dot positive or negative? Yep. So Q dot is negative 5 times 10 to the second watts. Now we can plug these in. Du dt is equal to negative 5 times 10 to the 2, and then minus a negative 1 times 10 to the third. So we get that du dt is equal to positive 5 times 10 to the second watts. Okay, so as time goes by, the internal energy is increasing at this rate. Now, second, we're asked for d little u dt. Well, we know that du dt is equal to 5 times 10 to the second, and that's equal to the mass times d little u dt. That's the boxed equation. And mass is given as 0.75. So d little u dt is equal to 666.67. And this is in units of watts per kilogram. And now we have this relationship. Now we're trying to find the specific internal energy as a function of time. What we have is that du dt is equal to 666.67. And we're given the specific internal energy at time 0. And so the way we're going to solve this is you can think of it as just we're integrating both sides. I like to think of it as this is called separation of variables, and you can do slightly more complicated differential equations with the same technique. But I'm going to multiply both sides by dt. So du is equal to 666.67 dt. And now I can integrate both sides because we have, one of those infinitesimal increments on both sides. And you get that u is equal to 666.67 t. That's what you get from integrating the right side, plus some constant of integration. And now we have to think about that initial condition, that boundary condition. So the boundary condition says at time equals 0, u is equal to 20 times 10 to the third. So I'm going to plug both of these values into the equation above, and I get 20 times 10 to the third is equal to 666.67 times 0 plus c. That can only hold if c is equal to 20 times 10 to the third. And so now I can update my function. This is the function here. That equation is still true. Now we just know what c is. So we have that u as a function of time is equal to 666.67 t plus 20 times 10 to the third. So with that equation, we can calculate what that specific internal energy would be at any time value after that initial case. Okay. Any questions about that?
We don't need to include units within constant.
Yeah, if you have a function like that, I guess if you were going to be clear about it, you could say t is in seconds and u is in joules per kilogram. Yep. But when you have functions like that, it's fine with me if you just leave it as the function. Any other questions about that one? Okay, so basically in the steady state cases, you never have to worry about functions of time. In the transient cases, it is possible mathematically to come up with functions, of time. That's not something I'm going to emphasize, but I do think there's one or two daily problems that ask you to do something like that. Okay. So now I want to just start giving, let's see, maybe we can finish this today. We'll see. I want to start giving an outline of topics so far. And each time I give these outlines, I'm going to sort of arrange things in different ways, have you try to sort of think about how these things relate to each other in different ways, sometimes more or less chronological, sometimes in sort of types of calculations. Okay, so the first thing we talked about was pressure. And first, we defined that pressure is equal to the force divided by the area that force is applied over, which means you can always calculate the total force applied by a pressure as the pressure times the area. And then second, we had our main pressure equation that everything else kind of derived from. So if a fluid is at rest and continuous, then the pressure at the lower altitude is equal to the pressure at the higher altitude plus the density of the fluid times 9.81, or the gravitational acceleration, times the difference in height between the high and low altitudes. And we got two things from this. We talked about manometers. And we talked about barometers. And both of those equations are just derived directly from the equation above that. Manometers are for calculating the pressure in an enclosed fluid. And barometers are for measuring the pressure of the atmosphere. Then we talked about temperature. So first, we talked about instantaneous temperatures. And we had the relationships, the temperature in Fahrenheit is equal to, let me just go right to 9/5 times the temperature in Celsius plus 32. And then the temperature in Celsius is the temperature in Kelvin plus temperature Celsius, no, minus 273.15. So that's if you're talking about temperatures at just a single instant, like temperature as a property. And then we talked about temperature changes. And those work a little differently. So the change in the temperature in Fahrenheit is 9/5 times the change in temperature in Celsius, but there's no additive constant. And the change in temperature in Celsius is the same as the change in temperature in Kelvin. So 0 Celsius is equal to 273 degrees Kelvin. But an increase of 1 degree Celsius is the same as an increase of 1 degree Kelvin. Third, we talked about the work of expansion. This really only pertains to gases. It's almost never worthwhile to calculate the work of expansion for a liquid because liquids are basically incompressible, and we'll use that fact a lot later on. But the work is equal to the integral from the initial volume to the final volume of P d volume notice this is the true volume. So if you're given volumes as specific volumes, you have to convert that. So not specific volume. This uses the first law sign convention. So once you calculate the integral, you can plug it right into the first law. And for sanity checks, it's always good to think about this. If the volume increases, that means that the work of expansion has to be positive. If the volume decreases, that means the work of expansion has to be negative. And if the volume is constant, that means the work of expansion has to be 0. To compute this integral, you need to have pressure expressed as a function of volume. Hold on a second. So to compute this integral, you need pressure as a function of volume. If you have pressure constant, that's even better. So if you ever have a case where you're given an equation, like in those polytropic processes where you can calculate pressure as a function of volume, or if you're told that pressure is constant, in the back of your mind, you should think, okay, it's going to be possible for me to calculate the work of expansion. Okay, you might not have to use it, but be aware that that's available as a tool. Okay, let's stop there, and I'm going to hand out the quizzes. Yes,
What do you mean by the P constant is better? Like it makes it easier?
makes it easier to do the integral. Yeah, you know, you don't have to deal with all the exponents and natural logs and stuff like that. That's all.